Good afternoon, Mayfield calculus students. This is Mr. Ray with our next and actually last vectors lesson in this course. Um, so this will be the only lesson that we do in Unit 4. Uh, the title for Unit 4 was Relationships Between Points, Lines, and Planes. So we're just covering one aspect of that, and that's we're looking at R3 and how a line might intersect with a plane, or how two lines might or might not intersect. Um, we're leaving out a pretty good portion of this unit. Um, Basically, how might two planes intersect, and even more complicated, how might three planes intersect? So uh, it's actually a fairly intensive section of lessons. Um, Unfortunately, due to obvious time constraints, we can't cover that. So uh, we're going to cover this, and so I'm basically going to merge uh, Unit 3 plus this lesson in Unit 4 into one unit, and I'll assess you from your assignment that will be sent available on Google Classroom on Friday afternoon, and you'll have until Sunday night to submit it. Okay, um, so um, So it's kind of like two separate topics here. We have a line intersecting with a plane, and then the other topic is a line intersecting with another line. Okay, so uh, if we look at, we have the different cases listed here, but it's almost quicker to look at a visual representation of that. So if I looked at a plane on a line, how might they intersect? There's actually three possible cases. Case number one, the line intersects the plane at a point. So there's our parallelogram plane pi, and the line actually goes through the plane and intersects at point P. You can see the dotted line that's actually below the plane. Okay, so that's a pretty common situation. Second case, the line is parallel to but does not intersect the plane pi. So basically it goes above or below depending on your perspective, but it's never going to actually touch the plane because it's parallel. Direction vectors are parallel here. Okay, so and then the third case that the line is actually on the plane. Okay, so um, let's um, let's look at some examples in this situation. You basically just remember the three cases, and you can kind of eliminate one or two cases depending on direction vectors and normals. And then there's some math to do to actually find if what the actual point is. Okay, for these two cases, there's not so much math, but this one there is. Okay, so if we go to the examples on the next page, first case, find the point of intersection, and that doesn't necessarily mean there is one, but that's for us to show whether it exists or not and what that point is. So remember, everything we're doing here, the lines are in R3. The planes obviously are in R3. So um, in the plane, sorry, we have this line here. Um, So it's got the one direction vector that shows it's a line. The fact that it's got three components in the direction vector means it's R3, and our plane pi is given in Cartesian as a Cartesian equation. So the first thing we can notice here is I'm going to compare whether these two things are parallel to each other or not. So first check I'm going to do is the line parallel, is L parallel to pi. So that's kind of short form to ask the question, are these two, is the line and the plane parallel? So notice in this case, we've got the direction vector of the line, um, and we have um, the normal for the plane because it's in Cartesian. So here we have, if I write this down, I've got n, which is the normal for the plane pi, that's equal to the a, b, c values in the Cartesian equation. So that's 5, -1, -4. And I can very easily get the normal, not the normal, the direction vector for the line. That's just equal to the direction vector that's in the vector equation. Okay, so that's important. So if I ask myself, are these two parallel? It's basically saying, because this is a normal and this is a direction vector, if I do the dot product between a normal and a direction vector, if the result is 0, that means the plane, the two things are parallel. Okay, so you have to kind of get your head around the fact that this is a normal and this is a direction vector. So this is already perpendicular to the plane. Okay, so if I do the dot product and it turns out to be 0, that means that these two are parallel. So I'm going to do the dot product. So if I do 5, -1, 4 dot 2, -1, 3, that's going to be equal to, that's going to be 10 plus 1 minus 12. I got the wrong value here. That's a -4. So it's 10 plus 1 minus 12. That's equal to -1. So therefore, the line is not parallel to the plane. Okay, so if I go back to my cases here of what can happen here, well, these two cases here, the line is parallel to the plane. When the line is on the plane, they're obviously parallel too. So basically I know that the line will intersect at a point because we've eliminated case 2 and case 3. Okay, so then the next thing we do is to find that point. So what we're going to do is, if I look at the line, I can come up with the parametric equations pretty easily. I've got x equals 1 plus 2t. I've got y equals -4 minus t, and z is equal to 0 plus 3t, so just 3t. Okay, so there's the parametric equations for the line. If I take I've got these values for x, y, and z, so I'm going to plug them into, substitute the parametric equations for the line into the Cartesian equation for the plane. So go back to the Cartesian equation of the plane. I've got 5, and I'm going to change the x into the parametric equation for the line, 1 plus 2t. And then I've got minus y, and y happens to be -4 minus t. And then minus 4z, z is 3t. And then minus 2 equals 0. Okay, so you can see we've only got the one variable here. So this is basically a linear equation now. So I'll just skip a few steps here. If I simplify everything here, I'm going to get -t equals -7, or t equals +7. Okay, and that tells me, that basically gives me the value of t that would be needed to plug into this equation here to make it be on the Cartesian equation of the plane. So now all I do is I use the fact that t equals 7 into the parametric equations of the line. So I've already got the parametric equations there, so it's x equals 1 plus 2t, so that's 1 plus 2 times 7, and that's equal to 15. Y is equal to, go back to here, I've got negative 4 minus t, so negative 4 minus 7, so that's negative 11. And then z is 3t, so that's 3 times 7 is 21. So those are the x, y, and z coordinates for the point. So therefore, the point of intersection is the point 15, negative 11, and 21. And if you wanted to check your work, you could always just plug this point into here to make sure it works. It will. Also, you could work backwards on the equation of the line and find the value of t again that would make this point work in this equation. Okay, so that's how you would, if you look back at the case, when there is a point of intersection, this is the technique that you would use. Okay. All right, so the next case here we have, again, find the point of intersection of the line, and again it's in vector equation form with the plane, which is in Cartesian equation, so very similar to the last question. Now, the fact that they throw this in at the end, if any, they didn't mention that in the first one, so it's almost like saying this one might not have an intersection point. So let's do the same thing we did on the other equation, on the other example. Okay, so again, the first thing we do is find out, is the line parallel to the plane? Okay, so again, let's summarize what we can get from this. So we know that for the line, that the direction vector is given directly to us in the equation. And for the plane, it's the normal that's given to us, and that's the coefficients of x, y, and z. So that's 1, 1, negative 1. So we have the same situation before. We've got the normal from the plane and the direction vector. I guess I should put where these are coming from. Normal from the plane, direction vector for the line. So again, if these are parallel, then the dot product of the normal with the direction vector would equal 0 if they're parallel. So let's do the dot product. 0, 1, 1, dot 1, 1, negative 1. So we're going to get a 0 plus 1 minus 1, that's equal to 0. So that tells us, confirms that therefore the line is parallel to the plane. Okay, so if we look at our three cases, we know it's not this one because in this case they're not parallel, but it could either be the line is on the plane, so every point on the line is an intersection point, or there's no intersection points because the direction, even though they're parallel, there's no points in common. Okay, so we still have to go through the same process in that. So let's, similar to what we did in example 1, we'll get the parametric equations from the line. So we get x equals, if we go back to here, x equals 1 plus 0t, so that's just x equals 1. Y is equal to 2 plus t, and z is equal to 3 plus t. Okay, and so we're going to substitute the parametric equations of the lines that are directly above us into the Cartesian equation of the plane. So we start with the Cartesian equation of the plane, so it's x plus y minus z. So x, well, that's just 1, plus y, well, y is 2 plus t, minus z, z is 3 plus t minus 3 equals 0. So again, equation with t's in, only one variable, so we should be able to solve this. Now what happens here is if I add up the t's, I've got a plus t there and a minus t there, so I actually have a 0t. Okay, and the number that comes up on the other side is a 3. 0t equals 3. So if you think about this, is there any value of t that would make this equation true? And the answer is definitely not, because so I can put this can never be true or not true. And since I can't find a value of t that works, when I plug this in, that means that the line is not on the plane. So therefore no POI. So that would have been the second case here. Okay, we knew they were parallel, but we could not find a value that would make any point on the line also be on the plane. So that we looked at those two cases there. Now we do have one more example, and you can probably guess which case that will be. So let's turn to that. Okay, so again, very familiar looking. Find the POI of the line, and that's in vector equation with the plane that's in Cartesian. So exactly the same style of question. Basically find which case it is and give the answer. So, sorry, I guess you can see that. So there's the equation of the line, vector equation form, and Cartesian for the plane. Okay, so again, first thing we're going to do is, here's the line. So this is the direction vector, so the direction vector m for the line, that's equal to 14, negative 5, negative 3, and the normal of the plane is equal to the ABC values in Cartesian form here, 1, 1, 3. So again, if I want to know if these two are parallel with each other, I'm going to take the dot product of the normal of one with the direction vector of the other. If it's 0, that means they're parallel. So very similar process. Is the line parallel to the plane? So again, we'll do the dot product. 14, negative 5, negative 3, dot 1, 1, 3. And so we're going to get 14 minus 5, that's a 9, and then minus 9. So we actually do get a 0. So in this case, they are parallel. Okay, so that's just, so far it looks like the second example, but if we look back at our cases, okay, so we've ruled out the first case for example 3 because they're either, the line is either on the plane or it never touches the plane, it's parallel to it. So we do the same process we did for example 2. Let's get the parametric equations of the line. So that's x equals 3 plus, so going back to here, 3 plus 14t, y is equal to negative 2 minus 5t, negative 2 minus 5t, z is equal to 1 minus 3t. And then, just like before, substitute the parametric equations of the line into the Cartesian equation of the plane. So start with the plane, we have x, so that's 3 plus 14t plus y, so the y is negative 2 minus 5t, plus 3z, and z is 1 minus 3t, and that's equal to 4. So if we simplify this all out, we end up getting 0t equals 0, which is obviously, we're not going to divide by 0 here because that's not allowed. But you think to yourself, is there any value of t that makes this true? And in fact, because that's a 0, it doesn't matter what t is, this will always be true. Okay, so it's not a specific value of t, it's all values of t. So what that tells you is basically every point on this line will be on the plane. No, sorry, that's true. So that line is actually on the plane. So we have the case 3 where the line is on the plane. So what's the point of intersection? Well, in this case, the point of intersection is the line that we're given. So we're not going to list some points. We're just going to say that the POI is the line. So we just go back and put the equation of the line again. Okay, so in this case, we were looking at how does a line intersect with a plane. We saw that there's 3 possible situations or cases that can happen, and we had 3 examples, 1 of each. So basically, we always start off by finding out how are these things parallel to each other or not, and then that allows us to eliminate 1 or 2 of these, and then we basically use our technique that you've seen to find the solution based on what cases are left. Okay, so that covers off intersection of a line and a plane. So what we're going to do now is look at the situation where we have 2 lines. Okay, so if you look at the picture, this is on your lesson note. In this case, in this situation, we have 4 cases. Okay, let's look at the 2 easiest to think about. Coincident lines, basically the 2 lines are exactly the same line. Okay, so what's the point of intersection? It's either line. Okay, the case where the 2 lines are parallel, but they don't meet. Okay, so there's no intersection for this case 3. This is the case, you'd think it'd be the most common, but in 3 space it's not usually very common. Most times 2 random lines will not meet. So in this case they do happen to meet at a point. And then the last case, this is where we introduce a new term, the word skew. Okay, so skew means, and we only use this in R3, it means the 2 lines are not parallel but don't meet. Okay, so both of these cases 3 and 4, they don't meet, but we have 2 different situations. One, the lines are parallel and don't meet, and the other one here, they're not parallel but they still don't meet. Okay, so let's look at, we're only going to look at 2 examples here. Okay, so find the point of intersection of the 2 lines. This line is in parametric equations, and this line is in symmetric equations. So this is the first time we've seen this. So what we're going to do is do the direction vectors for both of these. So the direction vector for line 1, if you remember from parametric equations, it's just the coefficient of the t terms here. So that's going to be 4, 1, 1, because that's the coefficient of the t's. Now this one, we've never really done this before. So the direction vector of line 2. You could turn these back into parametric equations, but there's a quick way of doing this. As long as you've got these things work the right way, you can just use the numbers on the bottom of the symmetric equations. Make sure you got your x, y, and z in the right place. Now this is a bit odd because there's nothing on the bottom. Now I'm going to actually rewrite that as it would be 2 minus z over 1, but we want to have the z positive, so it's actually going to be we're going to put the negative 1 on the bottom, and this would be a plus 1. Okay, so I'm going to, sorry, that's a 2. 2 doesn't really come into play. So that's how you can rewrite it, but the bottom line is most of the time you would have something you could use. If there's nothing on the bottom, it's either a 1 or a minus 1. So in this case, the direction vector is negative 3 to negative 1. Now, this time it's a little bit different because we have 2 direction vectors. So this time we're not going to take the dot product because if I took the dot product and it was 0, that would mean they're perpendicular. So the way I have to test if they're parallel is to see if one is a scalar multiple of the other. So if I was to write I could say that you can just visually see this, that you can't set this up, this equation up. There's nothing like you could check and say, okay, well, for the y coordinate, I could multiply by t could be 2, but that wouldn't work for this, and it definitely wouldn't work for that. So there's this equation actually can't work. So it means they're not scalar multiples. So therefore, the lines aren't parallel. So L1 and L2 are not parallel. Okay, so if we looked at our cases, the ones that aren't parallel, well, case 2 and 3 are parallel lines. Okay, so we're down to either case 1 or case 4. Either they intersect or they don't. Okay, so what we're going to do is look at the parametric equations. We've done this before earlier in this course. So if I look at the parametric equations, well, this one's already, first line is already in parametric, so I'm just going to write those out. For t, y is equal to 2 plus t, z is equal to 2 plus t, and L2, this is where you'd have to convert them back, but back to parametric equation. That's 2 minus 3s. Sorry, that's x equals, y equals negative 1 plus 2s, and z is equal to 2 minus s. Now what we do, you remember this, we set these equal to each other, so we have create like 3 different equations. So we're going to start with the x and y. So for the x coordinate, we basically say that 3 plus 4t is equal to 2 minus 3s. 3s. Okay, and for the y, we set these two equal to each other. 2 plus t is equal to negative 1 plus 2s. So what we're going to do, it's never really straightforward how to do this. You want to simplify these as much as you can. So when I simplify this, I get 3s plus 4t is equal to negative 1. When I simplify this, I get 2s minus t equals 3. Okay, now this is where your skills from grade 10 come in. You basically got two equations with two variables, so we want to solve for s and t. So you can use substitution or elimination. In this case, we definitely have to multiply because we can't just. Actually, no, we could arrange this for t. So t is equal to 2s minus 3, and then we could plug that into here. So I've got 3s plus 4 times t, which is 2s minus 3, equals negative 1. So I'm going to get 3s plus 8s minus 12 equals negative 1. 11s is equal to 11, so s is equal to 1. Thankfully, it's not a nasty looking fraction. And now I can take that value of s, plug it into here, so t would be equal to, I just plug the 1 in there, 2 minus 3, so that's a minus 1. So we've got values of s and t that work for the x and y coordinates. That doesn't mean that these are the correct values. We now have to check for the z coordinate. So we're going to plug these back in to these two equations. So, sorry, these two. So in the first equation, I got z equal 2 plus t, and the second equation, z equals 2 minus s. So when I plug my t value here, I get z equals 2 minus 1, which is equal to 1, and z second equation, I get s is 1, so that's 2 minus 1 also, which is also 1. So the fact that these two are the same means that those s and t values work for both equations. So is that our answer? No, this has just told us that there is a point of intersection, that they do meet. The fact that I was able to find values of s and t that match up, that work for both lines. So now what we do is we plug these values of s and t back in. We already know that z is equal to 1, but we need to find the x and y coordinates. So to get the x and y coordinates, you can use either one of the parametric equations from the two lines. So we'll use the first one, 3 plus 4t. T was negative 1, so x equals negative 1. Y is 2 plus t. T is negative 1, so that's 1. So we've got our three values, x, y, and z coordinates, so therefore we have a single point of intersection at the point, and make sure you put in the right order, negative 1, 1, and 1. So that's the answer there. So that does take a bit of work. We did something similar to this earlier in vectors when we were trying to find, trying to test if two lines were the same line, okay, or if they intersect. So one more example here, we've got this time find the point of intersection of these two lines, and in both cases here, L1 and L2, we've got both equations are parametric, so this is actually a little bit easier than the first one where we had to kind of struggle with the symmetric equations to turn them into parametric. So this time we've already got them done for us. So what we do have to do is come up with the direction vectors of both, which isn't that bad. So the direction vector of line 1 is equal to, if we look at line 1, you just look at the coefficient of the t, so it's 2, 3, 2. And then the direction vector of sorry, line 2, that's going to be 4, 5, 6. Okay, and if you try to see, let's do this in this order this time. Can I make an equation like this, where I have a scalar multiple? Can I create this vector from a scalar multiple of this? Well, for the first component to work, t would have to be 2. So if I multiply this by 2, I get 4, 6, 4. Well, that's obviously not the same, so this does not work. So the direction vectors are not scalar multiples of each other, which means they're not parallel. So that's our conclusion. Therefore, L1 is not parallel to L2. So again, we've eliminated these two cases 2 and 3. So either they're intersecting like the previous example, or they don't intersect. And you can probably guess what's going to happen here. Okay, so we're going to do the same thing as we did previously. We've got parametric equations for both lines. We're going to look at each coordinate separately, or each component separately. So for x, we've got 1 plus 2t is equal to 3 plus 4z. That should be an s. Sorry about that. 3 plus 4s. And the y, we've got 2 plus 3t is equal to 4 plus 5s. Okay, so again, I'm going to simplify these first. So if I simplify this, I get 2t minus 4s is equal to 2. Now one thing you can do, you notice all these are even numbers. I can actually divide this equation by 2, the whole thing. So if I divide by 2, I get t minus 2s is equal to 1, or t is equal to 2s plus 1. If I work on this one, I can get 3t minus 5s is equal to 2. Now what I'll do is I'll do a substitution here. So I'm going to plug this value of t into this equation. So 3 times 2s plus 1 minus 5s is equal to 2. And if I, sorry, 6s plus 3 minus 5s is equal to 2. If I simplify this, I get s is equal to negative 1. Okay, and now lots of arrows in this description. If I plug that s back into here now, I get t equals, I get negative 2 plus 1, so that's a negative 1. So I got values of s and t that work for the first two components, x and y. Now I have to check, so I guess I'll start up here, check for z. There's nothing that says you have to do x and y first and then check for z. Whatever looks easiest to do. So it's up to what you want to do. But you will find a solution for 2 of the equations and then check for the third. Okay, so for the first line, I've got z equals 2 plus 2t. And for the second line, I've got z equals 5 plus 4s. So, sorry, 5 plus 6s. If I plug my t in here, I get 2 minus 2, which means z equals 0. If I plug my s here, I get 5 minus 6, z equals negative 1. And you can see in this case they're not equal. So that means there is no value of s and t that will allow me to have a common point between the two lines. Okay, So therefore you can say there is no solution. And conclusion, they are skew lines. I would like you to use that word in this situation. And you could say no POI. Okay, so this is the case where there's skew and there's no intersection. This is the case where there is one intersection. So we only looked at two of these three cases, but the other two that we didn't do are fairly easy to find. In this case, in both cases actually, you'll find that the lines would be parallel. You can see the direction vectors would be scalar multiples in both cases. And then all you do is you would find a point, and in most cases you can find a point pretty easy. That's, for example, line 1, there's a point 1, 2, 2. You could plug that into the second line and see if that point's on that line, or you could take a point that you know is on line 2, 3, 4, 5, and see if that works. And if it's on the line, then you know that they're coincident. If you can't take a point on one line and show that it's on the other, it would be case 3. So we didn't really have to do these. You're just looking at find that they're parallel and then see if there's a common point on either one. Okay, so that kind of wraps up our vectors portion. So what I would like you to do is practice some of the homework from the 3 lessons that I've given you on video, and I've already posted the homework solutions so you can check your answers, and then I'll be issuing an assignment Friday afternoon that you will work on and then submit it online using Google Classroom and the PDF software that I've asked you to get for your phone. Basically, if you do it on a computer, you could scan it and find it, save it as a PDF. But most people don't have scanners, so you can use your phone, save it as a PDF, and then turn it in using that PDF form. I definitely only want one PDF file for each of your submissions. I don't want 6 different PDFs for each page, one for each page. So that won't be acceptable if you do that. So that, like I said, on an earlier Google Classroom post, there's several options that I gave there of software for your phone that does a good job of creating PDFs from pictures. Okay, so hopefully that wraps up our vectors. Hopefully you've got a fairly good idea how to find the intersection between 2 lines or a line in a plane. Okay, so the assignment that I'm giving is, and I've said this several times before, it's all of Unit 3, including the lessons that we did before the break in Unit 3, plus the 2 that we just did on video, plus the one that we just did now. So what we're going to do next week is we're going to start calculus. So I'll be posting a lesson Monday morning for you to get going on that. So good luck on your assignment, and as soon as I get them back, I will be handing it back to you online with a mark and hopefully annotated with, where you made mistakes or, your mark on each question. Okay, so have a good weekend and, have a good week. Hopefully I'll have maybe office hours where if you're having problems with some of the homework, you can sign into the chat and ask your questions then. Okay, thanks very much.